Hello everyone. Welcome to this live problem solving session for the course Introduction to Galois Theory. So we are in the third week now. So uh, let's write down the contents of the week 3 as a summary. So in this week we started with the Galois group. So we have defined Galois group of a field extension. So it is denoted by Galois group of K over F. So it is basically all those automorphisms which fixes the base field. So it is automorphisms of K such that sigma of A is A for all A belongs to A. We have defined this Galois group, and this basically forms a group. That is why it's called Galois group. Then we have seen one result like so as a summary it is like the Galois group of K over Kg is same as G. So what is this basically? So you start with a field K, you take a group, uh, you take a finite group G which is subset of the automorphism group. Okay, then you have this extension K over Kg, where Kg is the fixed field of the group G. Then you see the Galois group of this extension. Then it is same as this group G. So this is the statement. And as a corollary, we have seen that if we take two different groups, the automorphism group, then their fixed fields has to be different. They cannot be same. So let me write that. So different groups of automorphism cannot have same fixed field. So different subgroups of the automorphism group cannot have the same fixed field. So this is the corollary of the previous result. Then we have defined Galois extensions. So what is Galois extension? An extension K over F is Galois. So we are defining only finite Galois extension. So it is finite. It is Galois extension when uh, the base field is same as the fixed field of the Galois group. So this is the definition which we have used, and after this we have given a numerical characterization of Galois extension. So K over F is Galois if and only if the degree of this extension is same as the cardinality of the Galois group. So this is one equivalent characterization of the Galois extension. Next, we have seen some examples which are Galois, some of them are non-Galois, and how to find the Galois group and those things as which we have already seen in the previous tutorial also. Then to give different characterizations of Galois extensions, we have introduced normal extension. So we started with the three equivalent condition for a finite extension to be normal. So equivalent definitions of normal extensions. And we have remarked that Galois extensions are always normal, but converse need not be true. So we will see the proof later. And after this also we have seen certain examples of extensions which are normal, which are Galois, which are normal but not Galois, those kind of things. So there are then we have some problem sessions in which we have seen some properties of normal extensions, like normal extensions need not be transitive and those things. Okay, let me not write as properties. So normal extensions need not be transitive. And what about the intermediate normality of intermediate fields? That is also we have seen. Then we have seen that any finite extension can be again extended to a normal extension. So finite extensions can be further extended to normal extensions. And in one problem, we have seen that short exact sequence of Galois groups. So short exact sequence of Galois groups. So it is basically when you have a field tower of extension KLF, and in which all three are normal. So sorry, all these two extensions are normal. Then what is the relation between the Galois groups? And we have seen that there is a short exact sequence. After this, we have defined separability, the concept of separability. So separable extensions, and we have seen that every finite extension of a characteristic zero field or of a finite field is always separable, or more generally, a finite extension of a perfect field is always separable. Finite extension of a perfect field is always separable. And finally, we have given one more characterization of Galois extension, that K over F is Galois if and only if K is the splitting field of a separable polynomial over the base field. Of a separable polynomial over the base field F. And these are the all the topics of this week 3. Now let's solve some problems based on these topics. Okay, so first let's do some simple problems, but which will be useful later. So let F be a field and let Fx be a polynomial in the polynomial ring f of x. Okay, then okay, suppose alpha 1 up to alpha n uh, be the roots of fx in the algebraic closure of f. Then show that okay, also let k be the splitting field of let k be the splitting field of f over f. So then basically k is same as f attached with the roots alpha 1 up to alpha n, right? So this is one of the definitions of splitting field. Then prove that the Galois group of k over f uh, is isomorphic to a subgroup of the permutation group Sn. Okay, so we are taking a polynomial fx in the polynomial ring and let alpha 1 up to alpha n be the n roots of this polynomial in the algebraic closure of k. Then if we look at the splitting field of this polynomial, let's say k, and let's look at the Galois, then this Galois group has to be isomorphic to a subgroup of Sn. So where n is the number of roots. Okay, so let's prove this. So how to prove that this Galois group is isomorphic to a subgroup of Sn? So basically we need to define an injective group homomorphism from this Galois group to Sn, right? So that is one simple way to do this, but that is the target. So now how to do this? So 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 let sigma be an element of this Galois group. Then we know that this alpha 1 up to alpha n are the roots of fx, right? Now what happens if uh, if we apply this sigma to these roots? So my claim is, so sigma is a map from k to k, right? And alpha 1 up to alpha n, all these are elements lies in this field k. So if we restrict sigma to this set alpha 1 up to alpha n, then this map alpha 1 up to alpha n has to be a bijection. So I think we have seen this thing in the lectures, but it's important, so I'm mentioning this specifically. So how to prove this? That sigma restricted to this set is a bijection. So if we can prove this, then it's enough, right? So first let's prove this. So note that okay, I think we need to take so now we know f of alpha I is 0. So what about sigma of f of alpha I? So this is basically f of, sorry, this is also 0. So this is sigma of 0, this is 0. But what is this? So this is same as f of sigma I, sigma of alpha I. So this is because fx is a polynomial in f of x, and sigma fixes element of f. So sigma will fix the coefficient of f. So we can interchange f and sigma. So this implies sigma of alpha I is a root of f. So this implies sigma of alpha I is equals to some alpha j for some j. So that means this. So if we restrict sigma, so this element must map to this element itself. So this map is well defined. But sigma is an automorphism. So sigma in particular it is injective. So sigma is injective on this set also. So let me write down this. Thus sigma of image of this set under sigma has to be subset of this set. But sigma is injective. So sigma is injective on this set also. But this is a finite set. So since sigma is 1 1, so this subset has to be equality. So this map is a bijection. So this proves our claim. Okay, so now define phi from the Galois group of k over f to Sn. So how we will define this? So you take a element from the Galois group, and we can thought Sn as the symmetric group of alpha 1 up to alpha n, right? Then you just map it to just restriction, sigma restricted to this set alpha 1 up to alpha n. Then sigma is a permutation on this set. So this then phi is an injective group homomorphism. So proving this is an injective group homomorphism is a very trivial exercise. So I am leaving that. And this particularly this proves the problem. So Galois group has to be subgroup of Sn. Now, so Galois group has to be subgroup of Sn. So from this, one can immediately say about the order of the Galois group. So let me put that as remark. So in particular, if degree of f is n, then f can have at most n roots, right? Then f can have at most n roots. So the Galois group of the splitting field of f, uh, Galois group of k over f, so this Galois group, okay, let me write where k is a splitting field of f over f. So Galois group uh, is a subgroup of Sn. Thus, the order of the Galois group must divide n factorial. So this is a upper bound, general upper bound for the Galois group. So this will be useful. Okay, so let's do the next one. So again, let F be a field and let A be a non-zero element of the field. And suppose fx be a polynomial in fx, then show that fx and f of ax has the same splitting field. It have the same splitting field over the base field f. So we are taking two different polynomials and we are claiming that they have the same splitting field over the base field f. So how to do this? So what is the splitting field of fx? Let's see that first. So let alpha 1 up to alpha n be the roots of fx in the algebraic closure of f. Then uh, then the splitting field of f of x over f is basically f. So you attach these roots with the base field, right? So this is how the splitting field looks like. So this is the smallest field containing f and the roots alpha 1 up to alpha n. And what about the splitting field of f of x? How to write that one? So now note that, so alpha 1 by a dot dot up to alpha n by a are the roots of f of ax in f bar. So thus the splitting field of f of ax over f is so we know the roots, right? We know the roots of this polynomial. So just attach the roots to the base field. So this is the base field f. Now you attach the roots alpha 1 by a dot dot up to alpha n by a. But a is element of the field itself. So we can write this as it is just f of alpha 1 up to alpha n, because a belongs to f. Since a belongs to f, f will absorb its own elements. So these two fields are exactly equal. So this completes the proof. So these two polynomials has the same splitting field. So this thing is interesting. Sometimes we can scale and get the roots, and if we observe the proof, then we can have a similar type of result like this. So again, let f be a field. Okay, let me not write as a different problem. I will just write as a remark. Also, f of x and f of x plus a, these two polynomials also have the same splitting field. Have the same splitting field over the base field f. So here we have just multiplied by a, and here we are just adding a. So instead of alpha 1 by a, alpha n by a, we need to take alpha 1 minus a dot dot alpha n minus a. So this will be the roots of f of x plus a. And if you follow the same method, you can prove this result also. And more generally, if we combine these two, then f of x and f of ax plus b has the same splitting field. So it have the same splitting field where 0 not equals to a belongs to f and also b belongs to f. Okay, so this is easy to remember. So if you just make a linear change in the variable, it will not affect the splitting field. That's all. So we know from the characterization of normal extensions that finite normal extensions are basically splitting field of some polynomial. So that is one characterization of the normal extension. Now let's do some problem in the separability part. So separability is all about the multiplicity of roots. Means an irreducible polynomial is separable when it has all the roots of the polynomial are simple, right? So it has no multiple roots. But what happens if a polynomial has multiple roots? Then what will be the multiplicity of those roots? So let's see that one first. Okay, so I think I should define the multiplicity first. Then I will go to that problem. So let fx be a polynomial in fx and alpha be a root of f in f bar, right? Then the multiplicity of the root alpha in f is basically the number of times this root occurs. So in our language is maximum of all those in positive integer n such that x minus alpha power n divides fx, but x minus alpha power n plus 1 does not divides fx. Or equivalently, uh, alpha is a okay maximum of n such that uh, the nth derivative of f evaluated at alpha is 0, but alpha is not a root of the n plus 1th derivative. So alpha is a root of the nth derivative, but alpha is not a root of the n plus 1th derivative. So these two are equivalent. So this is basically, so alpha can be root up to m times, right? So that number is the multiplicity of the root. And if the multiplicity is 1, then it is simple root. Okay, now let's come to this problem. So this is problem number 3. So let f be a field and fx be an irreducible polynomial in f of x, and let k be the splitting field of small f over capital F. So that means K contains all the roots of the small f. Then show that uh, all the roots of small f, all the roots of small f have, have the same multiplicity. So all roots has to be of same multiplicity. So note that in this theorem, f is an irreducible polynomial. This thing is important. Without this thing, this statement is not true. So we may construct easy examples for that. But let's prove this first. So what is the statement is saying? Here you have a base field f. You are taking the splitting field of a polynomial over the base field f. Then in this splitting field, all the roots of f has the same multiplicity. So let a and b belongs to k, b. Okay, belongs to k is not required. It is trivial because all the roots has to lie in k. So be two distinct roots. Be two distinct roots of fx in k, and also let ma and mb be the multiplicities of a and b respectively. So what we want to prove now? So we want to prove ma is exactly equals to mb, right? This is what we want to prove. So since ma is the multiplicity of f, so we can write so note what is multiplicity? Maximum of n such that x minus alpha power n divides fx. So we can write fx is equals to x minus a power ma times some g of x. So for some gx belongs to kx, right? Now recall that how we define field homomorphisms. So note that there exists a f homomorphism, or we can take automorphism, because in case of algebraic extensions, f homomorphisms will be f automorphisms, that we have already proved. So there exists f automorphism uh, of k. Okay, let's put a name for this. Phi from k to k such that phi of a is equals to b. So here we have k. So we are taking a automorphism which sends a to the another root b. So that is possible, right? That we have already done. Then uh, phi of f of x is same as f of x, right? Because the coefficients of f are coming from the base field f, and elements of the base field are fixed by f. So phi of fx has to be f of x. But what is phi of fx? So this is phi of x minus a power ma times g of x, and under phi a is mapping to b. So this is same as x minus b power m of a to g of x. But this is same as our f of x. So this implies f of x can be written as x minus b times, sorry, x minus b power m of s times g of x. Okay, not exactly g of x, it is phi of g of x, because g, coefficient of g did not come from the base field x. So here the power is ma. So that means the multiplicity of b has to be at least a, m of a. So f has at least ma b roots. So from this we are getting mb is greater equals to m of a. Now if we interchange the role of a and b, so we will get another homomorphism phi prime which sends b to a, and repeating the same argument we will get ma is greater equals to mb. So from that we will get the equality. So let's write down that. Okay, now if we interchange the role of a and b in above, we will get multiplicity of a has to be multiplicity of b. So from this we are getting multiplicity of a has to be multiplicity of b. So this proves this statement. So for an irreducible polynomial, all the roots have to be uh, all the roots must have same multiplicity. So this thing is important, and I want to put this as a remark. We can also count the number of this multiplicity. So if the base field has characteristic 0, then this multiplicity has to be 1. Why? Because in case of characteristic 0, all finite extensions are separable. So all irreducible polynomials are separable. Uh, so all roots of f uh, has multiplicity 1. And if the characteristic is p, then all roots of f have multiplicity some p power r, where r is non-negative. If the base field is finite, then it has to be 1, then r has to be 0. But if it is not finite, then it can have roots which are not simple, which is multiplicity more than 1. But in that case, this multiplicity has to be some prime power. So this is one fact, this can be proved, but I don't want to go in that much detail. So let's just write it down as a information. Okay, now using this thing that all the roots have same multiplicity, we can also prove one interesting thing. So let's write down this. So this is problem number 4. So again I will use the same setup. So let fx be an irreducible polynomial over a field f, and suppose uh, the number of roots of f in f bar is n. Then show that this n must divide this degree of f. Okay, n has to be number of distinct roots. That is important. So this part is important. So number of distinct roots must divide the degree of the polynomial. So how to prove this? So uh, so we know that all the roots have same multiplicity. All the roots of f have the same multiplicity. Okay, let's say it is m and it has n distinct roots. So let's say alpha 1 up to alpha n, it has n distinct roots, but it has alpha 1 m times, alpha n m times. So total number of roots is n times m, and total number of roots has to be equal to the degree of m. So that means this n has to divide degree of f. Okay, then the total number of roots of f is n times m. So thus uh, degree of f has to n times m, and this implies n must divide degree of f, and this n is the number of distinct roots. Now also note that this multiplicity has also it also divides the degree of f. So that is also one observation. Okay, now let's move on. So while I was doing summary, I have mentioned one result, that any finite extension can be further extended to a normal extension. So there is a concept of normal closures. So I want to define that now. So what I am saying, that if you have a finite extension, so let k over f is a finite extension. So that means degree of k over f is finite. Then there exists uh, another field L which contains k, such that L over f is normal, and this is also a finite extension. So any finite extension can be further extended to a normal extension. And if we take smallest such extension, then it is called the normal closure. So let me define this, then I will prove its existence and also uniqueness. So let K over F be a finite extension. Then uh, the smallest field L which contains K such that L over F is normal is called the normal closure of the extension K over F. So let's prove its existence. Okay, so okay, let's take let L be the intersection of all fields, let's say K prime which contains K and K over F is normal. We know that such field exist that we have already proved, because any finite field can be further extended to a normal extension. So we are taking all such fields and let's take their intersection. Then clearly L is the smallest such extension, because intersection of normal extensions is also normal. Then L is a normal closure, because we have not proved the uniqueness till now. L is a normal closure of the extension K over F. And why it is? It is a normal closure. So first of all, L clearly contains K because it is intersection of all fields which contains K. So it in particular it has to contain K. And second of all, L over F is normal. This is because intersection of normal extensions is again normal. So this is a normal extension and it contains K. And why it is smallest? Because if you take any other such K prime, then K prime has to contain L. And third, L is smallest such that 1 and 2 holds. So altogether 3, it gives that L is the normal closure. So this proves the existence. Now uniqueness. Okay, so let uh, L and L prime be two normal closures of K over F. Then we need to prove that L is isomorphic to L prime. So it is unique up to field isomorphism. So we To prove that these two are isomorphic, we need to prove that, yeah, also note that these are finite extensions. So this L has to be finite. So let me put that as remark. Note that L over F is finite because we are just attaching roots. So in the problem we have seen that how to construct this L. Okay, now let's come back to this uniqueness. So to prove this, we will use the uniqueness. So here we have K, here we have F, here we have L, and here we have L prime, and here we have K, here we have F. Now, so this is also finite. This is also finite because the total is finite, and same for here also. So now let sigma from K to K be a field auto. Okay, we don't need from K to K. We need from F to F. Be a field automorphism. Now, by extension theorem, maybe we can take extension theorem 2. So by extension theorem, uh, sigma can be extended. So by extension theorem, this sigma can be extended to a homomorphism from L. So can be extended to sigma prime from L to F closer, right? And such that sigma prime restricted to F is basically sigma. So this is by extension theorem. We are just extending the field homomorphism. But since L over F is normal, so this will imply sigma prime L over F is also normal. It should contain K, right? So, so we need to take a F homomorphism of K. So let K to K be a F automorphism. So it restricted to K must be sigma is normal, and sigma prime of L also contains K. So, but L prime is also normal closure. But, okay, let me write but here. But L prime of L is a normal closure. Normal closure of K over F. So this will imply sigma prime L has to be subset of L prime. So this implies sigma prime is a from L to L prime is a F homomorphism. And also if we interchange the role of L and L prime, then we will get a reverse map. Now if we interchange the role of L and L prime, we will get another F homomorphism, let's say sigma double prime from L prime to L, right? So these are F homomorphism. Now I want to prove that this sigma prime and sigma double prime both are automorphisms, both are, sorry, isomorphisms. So how to do that? Now claim is sigma prime and compose with sigma double prime. So it is a map from L prime, right? So it is identity map on L prime, and sigma prime is identity map on L. Sorry, we don't need identity, we just need bijections. Okay, so just bijections are enough. Sigma prime is a bijection. So as okay, both are bijections, and sigma prime are bijection. So how to do this? So note that, so proof of this. So because sigma double prime, it is a map from L prime to L prime, and the other one, it is mapped from L to L, are F homomorphisms. And these, and since this degree are finite, this has to be F automorphism. So L prime over F is finite, and degree of L over F is also finite. So these two are F automorphisms. Since composing from both sides is giving bijections, so they are itself bijections. So thus sigma prime and sigma double prime are F isomorphisms. So this proves, hence L is isomorphic to L double prime. So up to isomorphisms, normal closures are unique. So we know that any finite extension can be extended to a normal extension, and smallest such extension is the normal closure. Okay, now let's move on. Now let's do a concrete problem. So maybe this is problem number 5. So for any prime number p and any non-zero element A belongs to the finite field of order p. So for any prime number p and any non-zero element A belongs to a p, prove that this polynomial defined by fx, defined by x power p minus x plus a belongs to fpx it is irreducible and separable over this FP, finite field with P elements. So we need to prove that this polynomial is irreducible and separable. So only two things. So what is special about this polynomial? So first we will prove that it is separable. Then we will go for the mm, irreducibility. Okay, so let's prove this. Solution. Okay. So first let's observe some general facts about this particular polynomial. So let alpha belongs to FP bar be some root of f of x. Okay. So this will imply f of alpha is equals to 0. In particular, alpha power p minus alpha plus a is equals to 0, because our polynomial is x power p minus x plus a. So now what about f of uh, alpha plus 1? So it is also alpha plus 1 whole power p minus alpha plus 1 plus a, right? But we are in characteristic p. So this is basically alpha power p plus 1 power p minus alpha minus 1 plus a. And this is same as alpha power p plus 1 minus alpha minus 1 plus a. And it is exactly equals to alpha power p minus alpha plus a. And we have already noted that this term is 0. So this is 0. So this means alpha plus 1 is also a root of f of x, right? So if alpha is a root, alpha plus 1 is also a root. So if we repeat this argument, then what we will get? So this implies alpha, alpha plus 1, alpha plus 2, dot dot up to alpha power p minus 1. These are so alpha power alpha plus p minus 1 are roots of f of x. So we have got p roots. Now note that all these roots are distinct, because alpha plus I equals to alpha plus j. This will imply j minus I is equals to 0. This will imply j is equals to I. So these roots are distinct. And since degree of fx is p and it has p distinct roots, so f is separable. So all of roots has multiplicity 1. It has only simple roots. So thus F is separable over F. So in particular, the base field is not important, but it is separable polynomial because it has all distinct roots. Because degree of F is P and it has P distinct roots. So this proves the separability. Now what about the irreducibility? So first we have proved that F is separable. Now we will prove that F is irreducible over the base field P. Okay, it is Fp. Now we will prove F is irreducible over the base field F of P. So how to prove this? So we need some steps. So let's do it step by step. So first thing, note that F has no roots in Fp. Because right, we know the roots. So these are the all roots. So suppose alpha plus I is a root of F lie in Fp. Okay, so we are assuming one root lie in Fp, then all other roots are also lie in Fp. So let's take it alpha. Then the other roots, then the other roots of F are alpha plus 1 dot dot up to alpha plus p minus 1. So this thing we have already observed. So hence all roots of F are in Fp. So this means only two things can happen. Either all roots are in Fp or none of the roots is in Fp. So if, and we know that these roots are distinct. So there are p roots. So this implies some root has to be 0, right? Because Fp is basically 0, 1 up to dot dot p minus 1, and it has all these p roots, distinct p roots. So one of the element has to be 0. But this will imply f of 0 is equals to 0. But what is f of 0? So our fx is, so our fx is this polynomial. So if we evaluate at 0, it is just a, and a is non-zero. So 0 cannot be a root. So this implies a is equals to 0. It is a contradiction. Thus, f has no root in Fp. So this is the first thing. So, so what is our goal? Our goal is to prove that f is irreducible over Fp. That means we cannot write f as product of other polynomials, product of non-constant polynomials. So since f has no root in Fp, since f has no root in fp, so f has no linear factor in fp, right? Having a linear factor is equivalent having a root. So f has no linear factor in fp. So thus every irreducible factor of f in fp must have degree at least 2, because it cannot be a linear factor in f. So its degree has to be 2, at least 2. So suppose, so the last part. So suppose f is not irreducible. So suppose fx is some gx times hx in fpx. So this will imply degree of g as well as degree of h at least 2 by our earlier, by the previous paragraph. So we already know the roots of f, how it looks like. So then how this hx looks like. So then this hx must look like some x minus alpha minus c1 dot dot some x minus alpha minus cd, where d is the degree of h, because all the roots of f are alpha to alpha plus 1 to alpha plus p minus 1. So h must contain some of the roots. So h must be of this form. So this is in fp bar of x. Okay, we cannot write this as in fpx. Now what is coefficient of x for d minus 1 here? Now the coefficient of x power d minus 1 in hx is, so here we have one term up to d term. So we need the coefficient of x power d minus 1. So observe that it is basically minus summation uh, alpha minus ci, where I is from 1 to d. So this is basically minus alpha d minus summation ci, I is from 1 to d. But this ci is just up to 0 1 p, right? Okay, so I should mention here where d is the degree, and this c1 up to cd must be subset of 0 up to p minus 1, which is fp, because that is we are getting from the roots, this thing. So ci's are subset of fp. So this term summation ci, this is also in fp. And this whole term is in fp, and summation ci, I from 1 to d, is also in fp. So this will imply alpha times d is in fp, but d, Now what does it mean? So alpha is not in P, but D is in P. So it will imply alpha is in P. So this is a contradiction. So either alpha is in, so I want to say, so from this we will get this either D is 0 or either alpha is in P. So we will get D modulo P is 0. So that means P divides D. But D is less equals to P, right? Because degree of fx is D and degree of hx, sorry, degree of fx is P and degree of fx is D. So D must be less equals to P. But we are getting P divides D. So it will imply D has to be equals to P. So this is a contradiction. So here we have got degree of G and H are at least 2. So this will imply degree of H must be strictly less than degree of F, which is P. This is a contradiction. So this is a contradiction. Since D is strictly less than P. Hence, we cannot write, uh, so what is contradicting? So we cannot write F like this in FPX. Hence, Fx is irreducible over Fp. So Fx is both separable and irreducible. So this completes the proof. Yeah, so we have done separability and normality and all those things. So maybe in the next problem solving session we can do some more examples about Galois extensions and this normal extension, these things. Then it will be more clear. Okay, I think this is enough for this week 3. So maybe we can stop today.